You know, there are some math problems that have been considered impossible to solve for centuries. I don't just mean they're hard, I mean they were thought to be fundamentally unsolvable. Today, we're going to dive into a method that claims it can crack one of these massive challenges, offering a totally new key for a very, very old lock. Let's see what it unlocks.
Just take a look at this beast. It's a 17th degree polynomial. And for nearly 200 years, the consensus in the math world has been that finding a precise, exact answer for an equation like this is impossible. You could get close, sure, but never perfect. Well, that might be about to change.
So here's our game plan for this explainer. We'll start with the problem itself, then look at why the old school methods just hit a brick wall. After that, we'll introduce a new symbolic key that promises a real solution. We'll watch it do its thing, and finally, we'll dig into what a breakthrough like this actually means.
Okay, so what makes this equation so ridiculously tough? It's not just all those big numbers. It's really about the kind of answer we're trying to find.
The goal here, the holy grail, is what's called an exact symbolic solution. Think back to the quadratic formula from school, right? It doesn't spit out some long, messy decimal that goes on forever. It gives you a perfect answer using symbols like a square root sign. That's what we want here, that same level of absolute precision for this monster problem. An answer with no rounding, no close enough, just the perfect truth.
For hundreds of years, mathematicians have really had two main tools in their toolbox for problems like this. But, as we're about to see, both of them lead to a dead end.
So on one side, you've got classical algebra. The big problem here is a famous proof called Abel's theorem, which showed that for most polynomials of degree 5 or higher, a neat little formula like the quadratic formula just doesn't exist. Period. It's a hard mathematical wall. Then on the other side, you've got numerical methods. This is where a computer basically makes a series of really smart guesses to get closer and closer to the answer. But that's the key word, closer. It only ever gives you an approximation, not the exact symbolic answer we're looking for.
And this is where our story takes a really fascinating turn. A new method, based on a theorem by Murad Sultan Ezouidi, suggests a way to just bypass these classic roadblocks altogether. It doesn't use radicals, it doesn't use guessing, it's a completely different way of looking at the problem.
Now, at the heart of this new method is a very specific process. I want you to think of it like a machine. You feed the problem in one side, it runs through a series of very well-defined steps, and it spits out a very specific kind of answer. Now, we're not going to get lost in the weeds of this formula, but we are going to look at the key parts that make it tick.
Let's break this machine down. It's got 4 key parts. First, these binomial coefficients act like little tuning knobs, adjusting the calculation at each step. Then, you have the degree term and the base coefficient, which basically pull in critical info from our original equation. But the real magic, the secret sauce, is the recursive term. It creates this incredible chain reaction. The result of step 1 becomes an ingredient for step 2, the result of step 2 feeds into step 3, and so on. Every single calculation builds directly on the one that came right before it.
So how does this actually work for our equation? Well, the theorem tells us to calculate a set of 17 symbolic coefficients, which we'll just call S, and each one is found using that same recursive formula we just saw.
All right, so the process kicks off with the very first coefficient, S sub 0. Once that's calculated, its value is used to help figure out S1, which is then used to find S2, and on it goes, all the way up to S16.
The first result is in. The coefficients S0 is calculated to be exactly 0.
Okay, the second calculation for S1 also turns out to be 0. And, well, a pattern seems to be emerging. The process continues, and the coefficients S2 all the way through S6 are all 0. At this point, you've got to be wondering, wait a minute, are they all going to be 0?
And then, bam, the pattern breaks. The 7th coefficient, S7, is not 0. It's this precise symbolic value. And what's so important here is that this isn't a decimal approximation. It's an exact value, which is precisely what the theorem promised it could deliver.
After this amazing breakthrough, the process keeps chugging along for all the rest of the coefficients, from SES8 all the way to the end, SES16.
And this is the final scorecard, which is just brilliant. Out of the 17 symbolic coefficients we needed to find, only 2 of them are non-zero, S7 and S15. The theorem has taken that massively complicated polynomial and distilled it all the way down to these 2 perfectly precise symbolic values. These are the keys that will unlock the exact roots of the equation.
So the process gives us these exact coefficients. But what does that really mean? What's the big deal here? Let's zoom out and look at the bigger picture.
The source material really hits the nail on the head. The claim is that this method isn't just another way to get close to the answer, it's a machine for generating the precise, solvable roots for problems that, until now, were pretty much filed away in the unsolvable cabinet.
So here's the bottom line. If this method holds up, it matters for three huge reasons. First, it directly challenges a mathematical belief that's been standing for nearly 200 years. Second, it replaces guesswork and approximation with a clear step-by-step process. And third, it gives us a tool to find perfectly exact answers where we seriously thought none existed.
And all of this leaves us with a really fascinating question to chew on. We've been looking at one very specific, very hard math problem, but the idea behind it is so much bigger. If a problem that has been labeled impossible for 2 centuries might actually have a solution after all, it really makes you wonder, right? What other impossible things have we written off too soon? What other problems are just sitting there, waiting for someone to come along and look at them in a completely new way?